Now we study an interesting problem. In the geometric application of partial derivative, we know that a surface which equation f(x)(0). Here f is a smooth, maybe for C1 omega. C1 function, okay? Here omega is an open set in Rn. Then if a point P is in S, this means capital Fp is 0. And we also assume that the gradient of f at the point P is not 0. That is, this is omega. And our S is a surface, and P is a point in S. P is here. So if the gradient is not 0, then we know that the gradient is a normal vector. Then the gradient is a normal vector. Why the gradient is a normal vector? Because the reason is that for any curve in S passing P, that is, here is S, P is a point here. So for every curve lying on S and passing through this point, the tangent vector of the curve at the point P is perpendicular to the gradient of capital F at the point P. Here S is the set f(x) to be 0. Okay, so this is the application of differential calculus for multivariable functions, a geometric application. The logic is that this gradient, using the chain rule, we can prove that this gradient vector at the point P is normal to every curve lying in S. Another curve passing to the point P, then the normal vector, the tangent vector, all these tangent vector are perpendicular to the gradient of capital F at the point P. So all the tangent vector of curves on S passing P lying in the same plane. This plane has a normal vector, that is the gradient of F at the point P. Okay, so but now we consider another question. Suppose a vector H is perpendicular to the gradient at P. Is there a curve in M passing P? Passing P means gamma 0 is P, such that the tangent of this curve at the point P is our H. So this is the question. Okay, I will show you. So this is S, and this is a normal vector. So suppose we have an H, H which is perpendicular to the gradient. Can you find a curve passing through the point P here, so that the tangent of the curve at the point is precisely our vector H? So this is an inverse problem for the application of gradient. of differential calculus. Previously, we know that the gradient is perpendicular to every curve lying in S, passing P, perpendicular to the tangent of every curve. Okay, but now if you have a vector perpendicular to the gradient, can you find a curve? So that this H is the tangent vector of that curve. Is there gamma such that the tangent of the curve at the point P is precisely this H. The condition is H normal to the gradient. So this problem is far from trivial, but it is an important and interesting problem. So we will study this problem here. So a more general problem is the following proposition. The conclusion is the answer is positive. The result is yes. The answer is yes, but we have a more general result. Let G be a continuously differentiable map from an Euclidean space to another Euclidean space, and P is a point in the zero set. That is, so G map Rm to Rn, the origin in Rn, the pre-image of the origin in Rn, that is G inverse 0, is a subset of Rm. This we consider as a surface. But of course, in general, this M might be very strange. But if we assume some regular assumption, so we assume that the rank of the metric of the derivative metric of G at the point P is N. Okay. Then the conclusion is that if G prime P is an N by M metric, therefore G prime P can be considered as a linear map from Rm to Rn. So if an H vector in Rm, which is acting by this linear map, is 0, then the conclusion is that there is a continuously differentiable curve, gamma, defined in a small interval around about 0, and taking value in our set M, such that gamma 0 is the point P, and the tangent vector of the point, the curve at P, that is the derivative of gamma at 0, is precisely our H here. So this proposition is what we want to prove now, very important and very useful. So why this proposition is a more general case of the previous problem about the H and the gradient of capital F. So let's so for our previous example, for our F, a function in Rm to R, so the P is a point in the inverse of the origin of 0. So then the derivative of F at P can be identified to the gradient at P. Okay. So the condition that H is perpendicular to the gradient vector is equivalent to the fact that the derivative of capital F at P acting on H is 0. So therefore, our previous consideration, geometric consideration, is a special case of this proposition. Okay. So this problem is not trivial and in fact very difficult, but we will prove this proposition as an application of the implicit function theorem. Okay. So let's prove this proposition. Our condition is that G is a map from Rm to Rn. Of course, you might also assume that G is defined over an open set in Rm, but for simplicity, we simply consider the Rm. And P is a point in the inverse of the origin. Okay, so this set is our M, which is a subset of Rm, of course. And the length of the derivative at P is N. And also our H, H is lying in the kernel of the linear map G prime P. That is G prime P, this metric acting on H is 0. So you should know that G prime P is N by M metric, and H is an M-dimensional, we consider as a column vector. Therefore, the multiplication of this is an N-dimensional vector. Okay, so this is the condition. We listed the condition here. Now we will show you how to apply the implicit function theorem. So G prime P is a metric. The entries of this matrix is G11, G1 M minus N, G1 M minus N plus 1, and G1 M, Gn1. G has n components. Therefore, the last row of this matrix is Gn M minus N, Gn M minus N plus 1, Gnm. Okay. All this Gij is the derivative with respect to xj for the ith component of G. Okay. So this metric, of course, all these partial derivatives are evaluated at the point P. So since we assume that this metric has rank n, the rank is n. Therefore, we may assume that the last n columns are linearly independent. We may assume that these last n columns independent. That is, the determinant of this metric Gij P. Here I is 1 to n, J is m minus n plus 1 to m. Okay, not 0. So this is, we might assume this condition. Because the rank of this metric is n, so without loss of generality, we assume that the last n column is linearly independent. Therefore, the corresponding determinant is not 0. Okay. So now we split our space Rm because this metric is n by m metric and the rank is m. This implies that m is not less than n. Okay, m is not less than n. M can equal to n. Then this means that if m equal to n, then the G prime n is a square metric. So the rank is n implies that this is an invertible metric. So from G prime pH is 0 from this condition, because the metric is invertible. the right upper corner, you see G point PH is 0. So if M equal N, then this G point P is a invertible square metric. So from this is 0, we conclude that H is 0. Now, H is 0, the result is trivial. Okay, because the curve we want, we can take as a constant curve. That is reduced to a point, so the derivative is 0. So the case M equal to N is trivial, and in fact, it also contained in our following argument.